Good evening, explorer, and welcome. You've arrived just in time. We're heading to the far side of the Milky Way, deep into the constellation Sagittarius, where a dead star no larger than a city has been sitting quietly in the dark for thousands of years, turning and turning and turning, 20 kilometers wide, holding inside it more compressed matter than the entire sun, dense enough that a single teaspoon of its surface would outweigh every mountain on Earth combined, smooth and dark and perfectly still. And yet the magnetic field wrapped around it is so violent, so unimaginably strong, that it has been slowly tearing the star apart from the inside, bending its solid crust the way you'd bend a piece of metal, millimeter by millimeter, for 42,000 years. Something finally gave way. But before we set off, every journey needs good company, so gently tap like and maybe even subscribe, and I'll keep the lantern lit. This will help other explorers find the sleepy universe. And in the comments, let me know if you could travel anywhere in the universe, where would you explore, and what's the one thing you'd bring with you? And before we leave, let's settle in and take a breath. All great journeys begin with a relaxing breath, so take a large inhale and a slow exhale and settle in, and if you happen to drift off, that's okay, we'll be here. Now, let's go explore the universe together. We're going to spend some time with SGR 1806-20, and with the day it cracked, and with every extraordinary thing that happened in the moments that followed, all the way from the far side of our galaxy to the upper edges of our own atmosphere. And with what scientists have discovered since, including a discovery made in 2025 that rewrote what we thought we knew about where the heavy elements in your body came from. But before we can understand December 27th, 2004, we need to understand what SGR 1806-20 actually is, because it's nothing like anything in ordinary experience, and the numbers that describe it require a little time to settle into. We're looking at a neutron star. And what is a neutron star exactly? And why should the words make something tighten in your chest just slightly? A physical alertness before you've even been given the details. A neutron star is what's left behind when a massive star, something between 8 and 20 times the mass of our Sun, burns through all its nuclear fuel and collapses. And the collapse is so sudden, so total, that the core, which had been the size of a region larger than the Sun itself, crushes down in less than a second into a ball roughly 20 kilometers across, about the same width as a medium-sized city, and the matter inside it is compressed to the same density as the nucleus of an atom, every proton squeezed together with every electron until they're forced to combine and become neutrons, and the result is an object so dense that a single teaspoon of it, if you could somehow lift it, would weigh around 1 billion tons, which is roughly the weight of every mountain in the Himalayas placed into a space the size of a sugar cube. It doesn't glow, it doesn't expand, it doesn't do anything you'd recognize. It just turns. And the turning is important because the turning is where the story of SGR 1806-20 begins. When the original star collapsed to form this neutron star, it did so while spinning, and the collapse compressed not just its mass, but its rotation, the same way an ice skater draws their arms in and spins faster, except instead of a slow, graceful movement, the star went from hundreds of thousands of kilometers across to 20 kilometers across in less than a second. And the spin rate exploded accordingly, and the magnetic field, which had been present in the original star and which grew in strength with every factor by which the star shrank, was now wrapped and twisted and amplified to something almost beyond comprehension. Here's a number to sit with. Earth's magnetic field, the one that guides compass needles and protects the planet from the solar wind, measures somewhere between 1/4 and 1/2 Gauss, and the Sun's magnetic field is between 1 and 5 Gauss, and those numbers feel comfortable and scaled to human experience, but SGR 1806-20's magnetic field, as of the last measurement, exceeds 1,000 trillion Gauss, which is a 10 followed by 15 zeros, and to give that number a consequence rather than just a length, that field is strong enough that if you were standing at the distance of the Moon from the Earth and SGR 1806-20 were sitting where the Earth is, its magnetic field would pull apart the electrons in every atom of your body before you could blink. It's the most magnetic object ever observed. Robert Duncan and Christopher Thompson first proposed the existence of objects like this in 1992, calling them magnetars, and they were a theorist's prediction before they were an observed reality. Two scientists working through the mathematics of what would happen to a neutron star that was born, spinning fast enough and hot enough for a particular kind of magnetic amplification process to take hold. A magneto-hydrodynamic dynamo that would convert the star's rotational energy and thermal energy into magnetic energy during its first seconds of existence, ratcheting the field up by a factor of 1,000 above what ordinary neutron stars possess, and the scientific community took years to fully accept that such things existed because the numbers felt like overreach, like theory running too far ahead of the universe's patience. The universe, it turns out, was not overreaching at all. SGR 1806-20 sits approximately 42,000 light-years from Earth, on the far side of the Milky Way, in a direction we can only see clearly using X-ray and radio telescopes because the dense band of interstellar gas and dust between us and it blocks ordinary visible light entirely, which means it is, to the naked human eye, completely invisible, hiding behind the galaxy's own body, announcing itself only by the high-energy radiation it periodically emits, which brings us to the name SGR stands for soft gamma repeater, which is the category of object it was placed in when it was first identified, a source of repeated bursts of gamma rays and hard X-rays, sporadic, unpredictable, patient between outbursts, but unmistakably periodic in its larger behavior. And how does it spin? Every 7.5 seconds. SGR 1806-20 completes one full rotation, which sounds slow compared to young pulsars that can spin hundreds of times a second, but for an object that is losing rotational energy to the constant drain of its magnetic field, the spin down is itself a measurement of how powerful that field is. The star gradually breaking against the drag of its own magnetism, and the rate at which it's slowing tells physicists the strength of the field that's breaking it. which is how they confirmed the measurement of that extraordinary 1,000 trillion Gauss number. So the star turns, and every 7.5 seconds it completes one slow, patient rotation in the permanent dark. Now we need to talk about what's inside it, because the interior of a neutron star is unlike anything else in the observable universe, and it's the interior that matters for understanding what happened on December 27, 2004. The outermost layer of a neutron star is its crust, and the crust is a crystalline lattice of atomic nuclei pressed into a solid structure roughly 1 kilometer thick, sitting above a region of increasingly exotic matter that deepens and changes as you move toward the core. And this crust is not the soft, yielding crust of a planet like Earth. Not the kind of material that shifts and fractures along fault lines to produce earthquakes of the kind that destroy cities. It is instead a material of almost incomprehensible rigidity, believed by physicists to be the strongest material anywhere in the known universe, hundreds of billions of times stronger than steel. The kind of material that would require forces of almost unimaginable magnitude to crack or shift, even by a fraction of a millimeter. And yet, as you go deeper into a neutron star, past the outer crust, the matter begins to transition through states that have no equivalent on Earth, regions where the nuclei begin to deform under the competing pressures of nuclear attraction and electromagnetic repulsion, taking on shapes that physicists have given the playful names of spaghetti, lasagna, and nuclear pasta, exotic geometries of ultra-dense matter that exist nowhere else. And below that lies the core, where matter is so compressed that we genuinely don't know with certainty what it is, whether it's a superfluid of neutrons flowing without friction, whether exotic particles called hyperons appear at the crushing pressures available there, whether stranger physics takes over entirely. And this is one of the reasons the December 27th event was so scientifically valuable, because the seismic ringing of a neutron star after a major starquake is one of the only tools astronomers have for probing what's inside. But the most important thing about the crust for our story is not its strength. It's the fact that in a magnetar, the magnetic field lines run straight through the crust, anchored to it, locked to it in a physical embrace so tight that any movement of the crust moves the field lines, and any shift in the field lines exerts a force on the crust. And because the interior magnetic field of SGR 1806-2, O is estimated to be even stronger than the external field that's already the most intense ever measured somewhere above 10,000 trillion Gauss deep inside. That internal field has been slowly, patiently, over thousands of years, applying stress to the crust from within, twisting it, building tension in it, accumulating strain the way a fault line on Earth accumulates strain between tectonic plates, except the forces involved are not the gentle creep of geological plates, but something like having the entire magnetic field of 10,000 suns pressing and twisting against a material that can barely give at all. The crust held for 42,000 years, and we know that number precisely, 42,000 years, because the radiation from the starquake that finally happened travels at the speed of light. And it took exactly 42,000 years to cross the galaxy between SGR 1806-20 and the small blue planet it would eventually, for a fraction of a second, wash over. That starquake happened in our late Stone Age. The light left before the first pyramid was built, before the wheel was invented, before writing, before cities, before agriculture, and it crossed the galaxy for the entire duration of what we call human history, and continued crossing the last of the distance, slowing for nothing, while every civilization rose and fell and the planet's surface changed. And it arrived at December 27th, 2004, at 21 hours and 30 minutes Universal Time, and struck every satellite in Earth orbit facing the direction of Sagittarius simultaneously. The initial spike lasted 0.2 of a second. 0.2 of a second. In that interval, the narrow fraction of a moment it takes to blink, SGR 1806-20 released as much energy as the Sun produces in 250,000 years. And to give that an anchor you can feel, the Sun is producing energy at a rate of approximately 400 trillion watts at this moment. The nuclear furnace of a star burning 4 million tons of hydrogen into helium every second, and it has been doing that for 4.5 billion years, and it will do it for another 5 billion years, and SGR 1806-20 produce the equivalent of 250,000 years of that output in 0.2 of a second, all of it in gamma rays and hard X-rays, all of it radiating outward from a body 20 kilometers wide. It's worth noticing, without forcing it, that this is the kind of number that doesn't quite fit inside ordinary thought, the kind that sits quietly in the mind and continues to expand long after you've moved on to the next thing. In terms of absolute brightness, measured in gamma rays from Earth, the burst reached an absolute magnitude of -29, which is roughly comparable in brightness across all of the galaxy's 200 billion stars combined, at the moment of peak intensity, and it outshone the full moon by a factor of 2, and it was detected by every X-ray and gamma-ray satellite then in orbit simultaneously, with one critical difference. Most of them were immediately blinded. The instruments aboard RIESI, which is the Ramati High Energy Solar Spectroscopic Imager, a satellite specifically designed to observe the brightest solar flares our own Sun produces, were saturated instantly, unable to measure the true peak intensity because the detector was overwhelmed, like trying to read a number by pointing a camera directly into the Sun. And similarly, Integral, the European Space Agency's gamma-ray observatory designed to study some of the most energetic events in the universe, was saturated during the initial spike, and the newly launched SWIFT satellite, built specifically to detect and study gamma-ray bursts from across the observable universe, had its detectors completely overwhelmed, even though it wasn't even pointing toward SGR 1806-20 at the time. The energy scattered enough across the sky to saturate instruments not aimed at the source. What saved the data from those first crucial fractions of a second was something nobody planned. A flotilla of ESA cluster satellites and the joint Chinese-European double-star mission, designed not for astrophysics at all, but for studying Earth's magnetosphere, happened to have particle detectors that could observe the early phase of the burst without saturation, and it was data from these satellites, instruments pointed at the wrong sky for the wrong purpose, that later provided the first earliest observational evidence of how the crust crack actually propagated. 3 distinct timescales within the first 100 milliseconds that matched the theoretical predictions for how a fracture runs through neutron star material, including an estimate of the crack's initial size, roughly 5 kilometers across. 5 kilometers of the hardest known material in the universe cracked. On a star 20 kilometers wide, imagine a crack 5 kilometers long, opening in a single snapping moment across the surface of something no larger than a city, with the force of 250,000 years of solar energy behind it. That's what happened. Gently tap subscribe, and I'll keep the lantern lit, for every journey needs good company. And tell me in the comments, if you could travel anywhere in the universe, where would you explore? And what's the one thing you'd bring with you? Now, the 3 timescales that ESA's instruments captured tell a more detailed story than the simple word crack implies. And they're worth sitting with because they reveal something about the physics that unfolded in those first 200 milliseconds. The first timescale was the initial onset, a rise in intensity that took less than 1/4 of a millisecond, which corresponds to the speed at which the fracture itself propagated through the crust. The crack opening at something approaching the speed that information can move through the crystalline material. Because in the neutron star crust, there's no softness to absorb and slow a rupture. The material is too rigid for that, and the energy of the crack moves through it at near the maximum speed the material's properties allow, which turns out to be very fast indeed. The second timescale was an exponential rise lasting roughly 5 milliseconds as the disruption spread outward from the initial fracture site across a larger region of the crust. The magnetic field lines anchored to that crust being wrenched violently from their previous geometry into a new, lower energy configuration. And the third timescale was a broader rise over approximately 70 milliseconds, corresponding to the propagation of Alfvén waves, which are waves that travel through magnetized plasma, rippling outward through the magnetosphere of the star, carrying the news of what had happened at the crust into the surrounding space. The total energy release in those first 200 milliseconds was, as the Nature paper published in April 2005 stated, approximately 2 × 10⁻46 ergs, or roughly 200 times the entire energy output of a typical SGR giant flare, and about 100 times the energy of the only 2 other giant flares ever recorded in the previous 35 years of monitoring. And there was still, after those 200 milliseconds, more than 5 minutes to go. Because the initial spike, the blinding galaxy-reaching wall of gamma-ray energy, was only the opening. After the main spike faded, a long tail of energy persisted, oscillating, pulsing, falling and rising in brightness with a very precise period of 7.56 seconds, which is the rotation rate of SGR 1806-20. And this is because what had happened after the crust cracked was that the enormous energy of the magnetic field reconfiguration had created what physicists call a trapped fireball. A hot bubble of electrons, positrons and gamma rays trapped against the surface of the magnetar by the very field that had just reconfigured itself, unable to escape instantly because the magnetic field was still intense enough to hold it. And as the star rotated, this fireball stuck to the surface at the site of the rupture, swept in and out of the line of sight of every detector in the solar system like a lighthouse beam, producing those precise, measurable pulses every 7.5 seconds for over 5 minutes, gradually fading as the electrons and positrons inside the fireball found each other and annihilated, particle by antiparticle, releasing their energy as gamma rays and slowly depleting the fireball from within. The entire X-ray tail lasted 380 seconds. For 6 minutes and 20 seconds, the dead star rang like a bell. And what arrived at Earth during those 6 minutes was enough to physically change our planet in measurable ways. The gamma rays hit the atmosphere, specifically the ionosphere, which is the upper layer of Earth's atmosphere, extending from roughly 60 kilometers to about 600 kilometers altitude, where ultraviolet light and X-rays from the sun normally ionize the gas molecules and create a layer of electrically charged plasma that reflects radio waves and enables long-distance radio communication. And this layer experiences a natural cycle between day and night, becoming more densely ionized on the side facing the sun and thinning on the dark side. And when the December 27th wave arrived, it hit the night side of Earth's ionosphere, and the effect was recorded on instruments across the globe. The night side ionosphere briefly became as ionized as the day side, as if the night had briefly become day, as if a second sun had switched on from 50,000 light-years away for a fraction of a minute. Victoria Caspi of McGill University in Montreal, who won the Hertzberg Medal in 2004 for her studies of magnetars, described it simply. The burst changed our ionosphere from night to day, and fishermen in the Arctic saw a sudden aurora at that moment. The aurora was the sky responding to a starquake on the far side of the Milky Way. The CHAMP satellite, a low-altitude German research mission designed to study Earth's own magnetic field, detected a modulated signal in its geomagnetic data with a period of exactly 7.5 seconds during the flare, a faint but measurable oscillation in Earth's magnetic field caused by the electrical currents induced in the ionosphere by the pulsing radiation. And the Demeter satellite, a French research satellite studying the electromagnetic environment around Earth, also detected the event in its energetic ion counters, and ground-based, very low-frequency radio monitoring stations around the globe recorded sudden ionospheric disturbance events simultaneously, all consistent in their timing and all pointing to the same direction in the sky, toward Sagittarius, toward the far side of the galaxy, toward a dead star nobody could see in visible light. The seismic energy equivalent of the starquake, calculated from the energy released, was magnitude 32 on the Richter scale, which is 32 sextillion times more powerful than the most powerful earthquake ever recorded on Earth, the 1960 Valdivia earthquake in Chile that rang the planet like a bell for days. And to hold that comparison for a moment, the entire surface energy of that Chilean earthquake, which toppled cities and generated a tsunami that crossed the Pacific, was 32 sextillion times smaller than what happened on the crust of SGR 1806-20 on December 27, 2004. And the star didn't move. It absorbed this event internally, released it externally, and continued turning every 7.5 seconds into the dark. Now we need to go deeper into what the science satellites captured in the hours, days, and weeks that followed, because the story of December 27th didn't end with the initial blast. And some of what came after reveals things about the universe that nobody had expected to find, things that have reshaped our understanding of where the atoms in your body actually came from. 6 days after the giant flare, Brian Gainsler at the Harvard-Smithsonian Center for Astrophysics and his team detected something remarkable using radio telescopes, including the Very Large Array in New Mexico. A radio afterglow, a fading radio nebula expanding outward from the position of SGR 1806-20. And this nebula was not just a faint smudge of emission, but a resolved, linearly polarized structure that was, by the time they observed it, already expanding at approximately a quarter of the speed of light. At a quarter of the speed of light. This is what the energy of the magnetic field reconfiguration had done to the space around the magnetar. It had blasted a cloud of magnetized plasma and relativistic particles outward into the surrounding interstellar medium fast enough that by day 6, the cloud was large enough to be resolved, its edges distinct, and by day 19 it had expanded further, the entire nebula growing visibly between observations and radio telescope networks in the United Kingdom, India, the Netherlands, Australia, and the United States all tracked this expanding bubble, and what they were measuring was the echo of December 27th, a physical aftershock propagating through the interstellar medium at a fraction of light speed, carrying outward the imprint of what had happened to the star's crust 42,000 years ago. The radio afterglow was 100 times larger than any previously detected afterglow of its kind. And hidden within it, in the data nobody fully understood at the time, was something that would only be properly identified 20 years later. Because the burst of December 27th had done something that the initial spike and the trapped fireball and the radio afterglow had not fully accounted for, it had ejected physical matter from the neutron star's crust. The seismic violence of the fracture, the 5-kilometer crack propagating across a surface of incomprehensible rigidity with the energy of 250,000 years of sunlight behind it, had not just rearranged the magnetic field and released energy into space, it had physically thrown crustal material outward at velocities greater than 10% of the speed of light, blasted chunks and showers of the most neutron-rich matter in the universe into the space around the star, and that matter, thrown outward at those speeds, was in exactly the conditions required for something called the rapid neutron capture process, or the R process, which is one of the 2 fundamental nuclear reactions responsible for building the heavy elements, the ones heavier than iron, that make up a significant part of the periodic table of elements and a significant part of everything in the world. The gold in any ring if you're wearing one right now. The uranium in every nuclear power plant. The platinum in every catalytic converter, the iodine in every thyroid gland. These elements cannot be built by ordinary stellar fusion, the hydrogen to helium burning that powers stars like our sun, because building them requires an environment so flooded with free neutrons and so violent in its energy that atomic nuclei can absorb neutron after neutron faster than they can decay, climbing up the periodic table in rapid steps to form the heavy elements that make chemistry rich and complex and biological life possible. And for decades, the question of where this process happens in the universe, where the conditions for our process nucleosynthesis actually occur, was genuinely open. a mystery sitting at the intersection of nuclear physics and astrophysics, with neutron star mergers as the leading candidate after the detection of gravitational waves from the GW170817 event in 2017, but with persistent evidence that mergers alone couldn't account for the total abundance of heavy elements observed in the galaxy's oldest stars. In January 2025, a team led by Anirudh Patel at Columbia University published a paper in the astrophysical journal Letters that matched a previously unexplained and largely forgotten hard gamma-ray signal detected in the hours after the December 27th flare, a delayed emission component peaking around 10 minutes after the initial spike and fading over the following hours, to the predicted signature of radioactive decay from freshly synthesized R process elements. The nuclear decay of heavy isotopes being created in real time in the ejected material from the crust. Their newly formed nuclei unstable and emitting gamma rays as they found their equilibrium configurations. The R process was happening. During the December 27th event, in the ejector thrown off by the cracking of the neutron star's crust, gold was being made, and uranium and platinum and all the complex heavy elements above iron synthesized in a fraction of a second, and then decaying towards stability, announcing themselves in a forest of gamma-ray lines that an instrument called Integral's ACS detector had captured in 2004 without knowing what it was looking at. Data sitting in archives for 20 years, waiting for the theoretical framework that would explain it. The researchers estimated that roughly 1/1,000,000th of a solar mass of R process elements was synthesized during the December 27th event, and they proposed that Magnetar giant flares of this kind may account for between 1 and 10% of the total galactic abundance of heavy elements, a contribution that fills part of the gap between what neutron star mergers can explain and what the oldest stars in the galaxy show us must have been present very early in cosmic history, when the universe was too young for many neutron star mergers to have occurred. Which means that some of the gold and platinum and iodine in the world around you right now may have been forged in events exactly like the one that happened on December 27th, 2004, far side of the Milky Way, in the crust of a dead star no bigger than a city. The science doesn't demand that this be moving. The fact just sits there, and it does its work. We're still watching SGR 1806-20. After the December 27th event, the Magnetar's behavior changed in ways that have been carefully tracked over the years since, its spin-down rate varying erratically in the months before and after the flare, its X-ray spectrum softening gradually compared to the hardening trend that had been building through the years preceding the event, as though the star had reached some kind of internal reorganization and was now settling toward a different equilibrium, and astronomers noted the change in the pulse profile, the shape of the oscillation in X-ray brightness as the star rotates, which shifted significantly after the flare and has remained in the altered state. And in 2024, a paper proposed something that, even in the context of everything we've discussed, might seem surprising: the periodic gamma-ray and X-ray bursts coming from SGR 1806-20 may be modulated by a planet in orbit around it, a rocky world of between 10 and 18 Earth masses following an orbit of 398 days, but with an eccentricity of 0.994, meaning it follows an almost impossibly elongated ellipse, sweeping close to the Magnetar and then retreating on a path that would make it the most eccentric planetary orbit ever proposed, and whether this planet, if it exists, was there before the original star died and managed somehow to survive the supernova that created the Magnetar, or whether it formed afterward in the debris of the explosion, remains entirely open, and the proposal is theoretical, requiring further confirmation, but it adds one more layer to a story that has never stopped surprising the people who study it. A dead star, twice the size of a city, the most magnetic object in the observable universe, turning once every 7.5 seconds in the dark, possibly with a world in orbit around it, 42,000 light-years away, waiting for the next time the tension in its crust builds past the point where the hardest known material can hold. The previous major giant flare before December 2004 was in August 1998. The one before that was in March 1979. Nobody knows when the next one will come. There's something honest in that admission, something that belongs at the heart of this story. We can understand the physics, we can model the mechanism, we can watch the satellite data in real time, and we still can't predict when a dead star on the far side of the Milky Way will crack again. The universe does not notify us. It just happens, and the light travels and it arrives. There's one more thing to notice before we let this story settle into the dark around you, and it concerns the question of what it means that we were here to record it. There are thought to be more than 1 million magnetars in the Milky Way, most of them long cold, their magnetic fields having decayed over tens of thousands of years from the extraordinary peak they reached at birth to something merely extreme, no longer capable of the starquakes that produce events like December 27th, now quiet and invisible and drifting through the galaxy without announcement. And among the ones still active, the ones still accumulating crustal stress, we've identified only 24 or so, and SGR 1806-20 is the most powerful of them, at the greatest known distance, and it still moved Earth's ionosphere from 50,000 light-years away. The nearest known magnetar to Earth is 9,000 light-years away in the constellation Carina. If an event equivalent to December 27th happened at that distance, it would deliver roughly 30 times more energy to Earth's upper atmosphere, and at 10 light-years, the models suggest it would destroy the ozone layer and trigger a mass extinction comparable to the worst in the planet's geological record. These are facts stated plainly, not for alarm, but for scale, because the universe contains these objects and they turn patient and quiet in the permanent dark, and the gap between the physics they embody and the ordinary world of sleeping and waking is simply very large. 42,000 years for the light to cross, 0.2 of a second of observable fury, a minute of ringing afterglow, and then the star turned back into the dark and continued its 7.5-second rotation and began, somewhere in the crystalline architecture of its crust, the long, slow accumulation of the next 42,000 years of magnetic stress. What we can say is that December 27, 2004 was the most energetic event recorded in our galaxy by any human instrument in 400 years, since Johannes Kepler watched the supernova SN 1604 brighten and fade with the naked eye from a world that had no satellite network to saturate, no ionosphere to flip from night to day, no radio afterglow detector arrays stretched across 5 continents to catch the echo of the dying crust. And the fact that we were here, with the instruments we happened to build, pointed in the directions we happened to point them, and that some of them were designed for entirely other purposes and captured this event by accident, feels like a small, genuine gift from the cosmos to the curious. Some days the universe sends a message you didn't know it was sending, and the instruments you built for something else are the ones that read it. We genuinely don't know what the interior of SGR 1806-20 is made of, not precisely, not at the core where the pressures exceed anything achievable in a laboratory and where the physics become speculative. And we don't know exactly how the magnetic field is structured deep inside, only that it's stronger than the already extraordinary surface measurement, and we don't know whether the planet proposed in 2024 really exists, or whether the modulation in its bursts has some other explanation. And we don't know when it will crack again, and we don't know whether there's a giant flare happening right now on some magnetar too far away for its light to have reached us yet. What we do know is that the 42,000-year-old light carried heavy elements with it, and that somewhere in the periodic table, in the heavier end of the column of elements, there's a fraction of abundance that came from events exactly like December 27th, from starquakes on dead stars in the dark, from crust fractures propagating in a quarter millisecond across the hardest known material, from trapped fireballs ringing like lighthouse beams while they slowly annihilated themselves. The universe makes gold in the quietest places. The star turns, still turning. 42,000 light-years away in the direction of Sagittarius, where the sky is dark and heavy with old interstellar gas, and the galaxy curves toward its densest center, and the star turns, 7.5 seconds per rotation, its crust building toward the next fracture by some fraction of a nanometer with each revolution. The internal magnetic field doing its slow geological work in the medium that makes geology look casual and patient, and the light from the next event is already on its way toward us, or it will be. Or perhaps it was thousands of years ago, and we won't know until the moment arrives. The ionosphere doesn't know what's coming. Neither do we, and there's a kind of peace in that, in the simple fact that the universe is larger and stranger than any single human attention can hold, and that dead stars turn in the dark and make gold and crack and send their light across the galaxy, and that sometimes we happen to be watching when it arrives. It's still out there, turning. But before we go, every journey needs good company. Gently tap subscribe, and I'll keep the lantern lit. And in the comments, if you could travel anywhere in the universe, where would you explore and what's the one thing you'd bring with you?